So I will sort of in a pictorial way go through the major developments in quantum mechanics, starting from early 1900, namely Planck's discovery of Planck's formula, and see and come up to the present level and sort of try to find out what are the ideas which has found application now, so that the relevant developments now beginning to find application in quantum technology will be evident, and some more other developments maybe will find application in future. So I will sort of walk you through these developments of quantum mechanics and their application into quantum computation right now. So this will be an overview kind of thing. So I will literally follow, these pictures. So not too much of mathematics. So the real heroes in the development of quantum mechanics are Schrödinger, Heisenberg, and then Dirac. Dirac for relativistic quantum mechanics. This non-relativistic quantum mechanics is Heisenberg, just as he is in the middle place, then Schrödinger. But as has been told by Newton, they stand on the shoulders of giants. So investigation of light, and its properties started in different laboratories in Europe. And interference, diffraction, and essentially through light, behavior of light is that the quantum mechanics have been born. So interference and diffraction that led to wave nature. Newton had this particle nature in mind. So there was always a duality between particle and quantum nature, which finally we have to accept that the quantum world is actually dual, both the natures are present. And what is the precise theory of quantum mechanics? There are various kinds of interpretation. For example, is it wave, is it particle? Is it like a pilot wave theory where the particle is sitting on a wave? All these phenomena have been kept alive by experiments. But predictions of quantum mechanics so far has hold true. So now, as you know, for example, Planck was trying to understand this, the black body radiation. Very simple thing. There is a, black ball. Inside that, photons are there. They are at thermal equilibrium. You make a small hole. The photons are coming out, and you find out, how many photons per unit area per unit time as a function of temperature. Beautiful. In the beginning, they will rise at some temperature. It will peak, then it will die down. Planck distribution law. So answer was known on the low energy side, on the high energy side. Low energy means lambda. And then small lambda is high frequency. So Planck sort of came up with an interpolation formula, very beautiful formula, essentially having this factor: density of states, how many states are there to be occupied between the frequency nu and nu plus delta nu. So that formula was derived in the classical world, quote unquote, using the wave idea of wave and boundary condition. Then the distribution part, which was 1 over h bar omega or h nu by kt minus 1. So exponential has to be dimensionless. So kt was already known. K is Boltzmann's constant. T is temperature. Average energy is kt. H nu was Planck's contribution. And we found out that this Planck's constant, if you don't put, things don't match. So the constant h came in. H nu by kt minus 1. 1 over. So again, that had two factors. This, factor which was giving distribution of photons as a function of temperature. And of course, you can see at very high temperature, you can neglect 1, it becomes exponential minus E by kt. E is the famous Boltzmann factor. So all this, as I told you, this sort of standing on the legs of giants, Boltzmann had come up with this factor, exponential minus E by kt. Of course, he did not know that E is equal to h. And for example, people who are trying to integrate over momentum, they always needed a constant. The people who used to do statistical mechanics, they have this phase space, dx dp. Now, to do the integration, they have to divide it by some constant. So h was some unknown constant having dimension of action. It was needed to define statistical mechanics properly in the phase space. So therefore, you can imagine h Planck's constant arose as a dimensionful quantity to define an integration properly. Now, only when Planck gave that formula, you could see that all these things fitted nicely. So this Planck distribution law, particularly that factor 1 over h nu by kt minus 1. People tried to derive various ways. Einstein tried his way. Finally, it was our recent boss, as Paul Roy had pointed out, who came up with perfectly from counting argument. That counting argument is generalization of Boltzmann's counting argument when he derived his partition function. This idea of number of partitions and quote unquote how much of ways you can partition, completely counting, that is so remarkable. That, for example, entropy is, this Boltzmann's formula, K log of omega. Omega is the number of partitions. Introduction of log. And the formula that log AB is log A plus log B. Properties of extensive property. So importance of exponential and log. And, dimensionful factor exponential has to be dimensionless, h nu by kt. So beautifully, merger of mathematics and physics giving rise to ideas and this information idea that counting, how many you can partition. That's a very beautiful concept by Boltzmann, which subsequently was used by all the practitioners, like Bose, for example, allowed that in a given box, as many number of particles can stay. Using the partition of n particles in k boxes with this freedom that as many number can be there in one box gave rise to that formula, which is 1 over h nu by kt minus 1, Planck's law. And you can imagine that photon is massless, no mass. So without any problem, if you supply energy, you can create any number. So there is no number conservation. So therefore, there was no chemical potential. So when Bose wrote that paper, very small paper, sitting in Dhaka University, sent it to Einstein, Einstein could immediately see that these so-called bosonic particles having spin either 0, 1, 2, 3, 4 integral. They are now called bosons. So he said that there are atoms, molecules which are also having integral spin. What's the difference between them and the photon? Difference is mass. So, but a particle having mass, you cannot create any number. You have to give at least that much of energy, mc square, to create it. So chemistry people knew it earlier. They had something called chemical potential, balancing of chemical potential in chemical reactions. So Einstein immediately could see that he has to put this factor. So each was exponential E minus mu by kt. Mu is a chemical potential. Statistical mechanics people already knew this in the form of canonical partition function, grand canonical partition function, which allows any number of particles to come in and go out. So the chemistry people had observed this fact that in chemical reaction you need some chemical potential. You see all these things join in Einstein's simple introduction of E minus mu by kt. But then Einstein was not a genius for anything, nothing. So he realized that E minus mu by kt minus 1, when E is equal to mu, or tending towards mu, this factor becomes 1, E equals 0 by kt. 1 minus 1 can become 0 at the denominator, so the whole thing blows up. So he realized it leads to a very interesting phenomenon, which is now called Bose-Einstein condensate. So he suggested that this is real, that is divergence, but if you integrate the total thing, it is finite, total number of particles is n. So very beautifully, he separated out the divergence part from the other part, came up with this idea of condensation. If some of you are curious, please read this Einstein's argument, how it predicted this phase transition. Just work of sheer genius by dimensional grounds, separating out the singularity part of an integral, calling it n0, use of that part which is called condensing at zero momentum, namely delta function. Beautiful derivation leading to this fact, and he predicted liquid helium would be the thing where liquid helium, when that phase came out, people apply this, that is a Bose-Einstein condensate. But it's a strongly interactive system. So Einstein never considered interaction. So there was a critical temperature, there was a quantum phase, but it was not very clear, it was not very clean realization. But now you can see why I'm talking about Bose-Einstein condensate, because now Bose-Einstein condensate and its phenomena which in charged particle is your superconductivity are now being used for quantum computation. So we will need macroscopic quantum object to design a quantum computer so that it stands and works at reasonable temperature. Reasonable temperature could be below liquid nitrogen, could be liquid helium. Now, maybe at higher temperatures, but you should have a quantum state. So these Bose-Einstein condensate and superconductivity. The relationship between them is Bose-Einstein condensate is a neutral particle. Superconductivity is a charged particle, Cooper pair. Both are now being used for quantum computation. IBM and other platforms are explicitly using superconducting qubits with something called circuit QED mathematics from Yale University and designing their quantum computer. Bose-Einstein condensate is beginning to enter. But Bose-Einstein condensate is at much lower temperature, so that creates the problem. Now, again, to quote Paul Roy, he pointed out that photon condensate has been realized, slightly different system, and at room temperature. So who knows, tomorrow, because this real photon light condensate has been observed, it may find technological applications. So therefore, the first development, namely Planck's distribution, in the hands of Bose and Einstein, got into this condensation phenomena, which is now giving us this quantum object like Bose-Einstein condensate and superconductivity to design quantum computer. Then photoelectric net, Einstein's beautiful paper, 1905. So basically established the particle nature. One electron goes, one electron comes out. Now those are the things which we are now using for measurement. So source of single photon, source of single electron, quantum dot, where you can put one electron through Coulomb blockade. Those are really becoming technology. So they're managing, handling this quantum individually, single photon, single electron, and how to localize them. These are the problems which are tackling now. Now, so then, Niels Bohr, for example, as you know, the early founder of quantum mechanics, came up with the idea of, the Bohr's atom, where electrons were moving in stationary orbits. There were some logical inconsistency there that particles in stationary orbit are still accelerating. They should emit radiation. Why it is not happening? That led to Heisenberg and Schrödinger to develop quantum mechanics. Heisenberg saw matrices in it, and Schrödinger saw differential equation. Now you see, so beautiful that this matrix mechanics, which came in the context of hydrogen atom, is the one which we are using now in qubits. So qubit was essentially because of discovery of spin, and the mathematical description was due to Pauli. That is the one which we are using now, discrete states, to build quantum computers, IBM quantum experience. So this kind of mathematics came from spin, and matrices came through Heisenberg. Heisenberg was a very intuitive physicist. He fortunately had taken a course on matrices. When he found out that the things that are being observed is an actual matrix element of Hamiltonian, he realized that this object, H expectation value of or matrix element between M and N is a matrix. So he very intuitively realized that he has taken this course and he brought matrices which naturally describe quantum mechanics. So in the same summer, Schrödinger came up with two beautiful papers. He took this Hamilton-Jacobi theory of classical mechanics and just one slight modification gave him his quantum mechanics, and he solved Schrödinger equation problem. If you read that paper, eye-opening, minus 13.6 by n squared. And the mathematics of Laguerre polynomials was already known in the context of vector space, Hilbert space. So you can see the mathematics of continuous variables which we are using now, that vector space, and linearity of quantum mechanics. That mathematics was already developed. That space was Hilbert space. Square, psi star psi, mod square is equal to 1. So one side is discrete matrices, easy to handle. Spins, any two-level systems, we are now using it for quantum computer. This, you heard about CAT state, coherent state, Professor Agarwal and many other people are talking about. That those are continuous variable states, infinite degree of freedom. We are beginning to learn how to use them. So-called CAT code and other continuous variable quantum computational platforms are now beginning to enter into practical domain. So now Dirac was a great synthesizer. He realized that these are actually manifestations of a abstract description called bracket. So see, bracket notation you have seen routinely now. What is the advantage of bracket notation? You can formulate quantum mechanics in an abstract way. Wave functions becomes its projection of coordinate space. Fourier transform becomes its projection of momentum space, but you can deal quantum mechanics in a space-independent manner. So therefore, and believe it or not, this thing what mathematics which you are using to describe a quantum bit density matrix was already there. So that mathematics to describe partially polarized light. And these two objects, identity, sigma x, sigma y, sigma z, whom we are encountering in describing the spin, were already known to Hamilton in the context of number theory. They are called quaternions. Hamilton at a very young age, claiming around 17, was taking a walk in a park. He was trying to generalize complex variables. He realized that complex variables is a generalization of real numbers, two real numbers, and which joined together by an object called I, so that I square is equal to -1. Then he said, how can I generalize it? So he generalized to pairs of complex numbers. But pairs of complex numbers cannot be written with elements like real elements where x, y is equal to ix. Namely, they commute. He realized these abstract numbers like I, j, k, what he needs to describe this so-called quaternions pair of complex numbers are such that sigma 1, sigma 2 is equal to minus sigma 2, sigma 1, anti-commuting numbers. And he just wrote it down on a bridge through which he was walking, so that you remember it. Somewhere in Ireland, apparently it is still preserved, that's what they say. And that is how abstractly this mathematics will describe spin, so-called quaternions, was born. So centuries later, Wolfgang Pauli reinvents these things, puts a factor based by 2, they describe the quantum world of spin. Similarly, Hamilton wrote a theory of light. When he tried to publish it, it was not accepted. So she called Hamilton-Jacobi theory. He made it into theory of mechanics, and that is the Hamilton-Jacobi theory. Therefore, you can see why Schrödinger in one step came from the classical world to quantum world, because it was through Hamilton-Jacobi theory. Hamilton described a wave front kind of a class of trajectories, not one particle. You see, the deep root of quantum mechanics is there in the classical world and also statistical mechanics. That concept of entropy, not adding up properly, when you take two equivalent gases, like for example, hydrogen atom of same kind of gas, partition into two different chambers, join them, and if you don't formulate things properly by dividing by an additional factor of n factorial, extensivity of entropy was a problem. So that was what we realized with large number of atoms, that n factorial division was understood when quantum mechanics came, that your electrons or photons will be described by antisymmetric wave functions or symmetric one. Only one out of n factorial space available to you. So you see, and through the phase space dq to dq integration, you needed a constant with the dimension of Planck's constant. All those hints were there. Mathematics was developed, Hamilton-Jacobi theory, quaternions, and then differential equation, like Fermi, Lagrange, they were all known. So now, anybody want to do great things, you should look up, have great friendship with mathematics people, and you can learn new mathematics, which probably you can use in the theory which is going to come up in future. Dirac was an electrical engineer, very shy, and he sort of had an abstract bent of mind, as you can see, through this bracket rotation. And he came to those days, Niels Bohr was the founder of this quantum interpretation of quantum world. So all these young people used to gather there. Dirac, Heisenberg, Landau, and Bohr. Everybody was coming there. So then, there two things come up with this correspondence principle, how to go from quantum world to classical world. We are still struggling with that. You can see many, many papers, people talking about the transition from quantum to classical. In naive ways, H bar goes to 0 limit. But for example, Vivek talked about coherent state, which are sort of classical. You take superposition of quantum states come up with some object which is S-bar independent, and it becomes classical. And who is the person who contributed to that mathematics? George Sudarshan. A precise mathematical way of showing how to come from quantum to classical. Okay. So if you are more curious, there is a very beautiful book, on coherent state and other aspects of quantum mechanics. You should look up the works of George Sudarshan. Sudarshan and Duck, a book on quantum mechanics, deals with many novel aspects. And then, Sudarshan's articles on coherent state, because he was the founder, clearly points out a very precise correspondence between classical and quantum, which is being used now. Its P function was used to show a very peculiar quantum correlation in a very recent paper, 2021, physically later. One of the authors is Vogel, EOGEL, you can search. It doesn't have this entanglement, it doesn't have this, it doesn't have that, but still it is quantum. What use it is? They have done an experiment using light to show that it's still useful, how to create them. Like, Davidovich, Professor overall, they were telling simple arrangement using beam splitters, half-wave plate, quarter-wave plate to show here the state of light, which is described through Sudarshan's P function, which is quantum, yet doesn't have the correlations like, squeezing, entanglement, those kind of things. So quantum world is very peculiar. Even now also we are trying to understand it. So you can see, so this correspondence principle and collapse of the wave function, that's still being investigated. For example, you have heard about collapse of the wave function. I'll show you the practical application of that, in one of those things like teleportation. So measurement and collapse. That some aspects I had told you, that if the spin is along z direction, if you measure along x and y directions, you will find still the spin existing there. Classically, it shouldn't be because it's 90 degrees, but quantum mechanical depth. So that was Niels Bohr's contribution from that correspondence principle and quantum mechanical interpretation due to Niels Bohr and his collaborators, so-called Copenhagen interpretation of quantum mechanics. So that has played a very significant role to the extent that the quantum computation algorithm, which is a new paradigm of computation, which is measurement-based quantum computation, which has come into existence. And many questions are arising about how do a function collapse. For example, even now, Roger Penrose, Nobel laureate of 2020, thinks that gravitation plays a very key role in collapse of the wave function. Many deep thinkers think that consciousness plays a key role. Therefore, many of these Bell state experiments tries to avoid, so makes it loophole-free test. Human consciousness, human will do not play a key role. You can see to what extent people have gone to test quantum mechanics. So very good. So these two aspects which came from their correspondence principle and this collapse of the wave function are very crucial from there. So that led, and 25, 26 around that, mathematical formulation came, which of course we are using in the evolution either through particle differential equation or through matrices. And then Dirac unified them. His book of 1932, people quote even now, his famous sentence in the first chapter that a single particle can interfere with itself. Double slit experiment. Till now also, people are trying to understand various interpretations with measurement, collapse of the wave function. Still, there is enough ambiguity there. Dirac's book more or less is complete. Many of these people who are key founders, workers in this area, still quote from that book and try to interpret interference of one photon with itself. Very recently, I heard talks of Professor Berlin, Professor Oral, for example, used to emphasize that part. And many, deep thinkers still look at double slit experiment and try to interpret it. Recently, for example, you should look up papers of Alok Pan, who is a co-organizer here. And he has a very beautiful interpretation of this double slit experiment in terms of weak measurement, weak value, like Weidman was talking about. Okay. And Professor Qureshi's work, you can see, for example, people are talking about uncertainty. Those are the kind of discussions which Einstein and Bohr had. Even now also there are surprises there. So anyway, mathematical formulation, besides, questions, those are all asked. And at that time, for example, Einstein realized the singlet state, like the state of 2 electrons in hydrogen molecule or 2 electrons in helium. They can, hydrogen, for example, you have para and also hydrogen. So these are the Bell states involved in space. So Einstein, Podolsky and Rosen realized that there is a non-local correlation and which they do not understand. So they claimed there should be a better way of understanding it. God cannot play dice. So then there was a series of correspondence between Einstein and Niels Bohr, many other people. Schrödinger came up with this word entanglement, very smart person. And he understood that there is some additional thing. So this steering, entanglement, those are, and coherent state. You should see he has a paper on coherent state. Amazing ideas and amazingly creative person. So then only when engineers came, like in Bell Lab, so entanglement, this non-local correlation was used for quantum work, namely teleportation and many other things. Collapse of the wave function. Again, engineers, Bennett and Brassard, 84, gave quantum key distribution using that. So those are also now become technology. Collapse of the wave function in 80s, then 90s, early 90s, the entanglement for teleportation in hands of engineers, Bennett, Brassard and others, Bennett and Brassard. You see, physics people are basically dreamers. So come up with theories. Application comes when engineers come. So therefore, those EPR paradox, so-called paradox, led to more developments, particularly Bohm's. In 50s, Bohm came up with this spider web theory and introduced spin variables, 2 degrees of freedom, to describe EPR paradox. That was what led Bell to develop his inequality in 60s, early 60s. You see, these kind of questions, then precise formulation, coming up with a model which is tractable, and then coming up with an identity which will test the reality of fundamentals. Thanks to Bell. And here basically, see, Bell was a person doing field theory particle physics. Okay. So some of these people bring ideas from other areas and use it here. And you see, this kind of thing which many of people have described in terms of probability, Bell, what he used was the result of a person called Boone, a statistics person. He had that -2 to +2 based on probability theory, more like century before. Bell pointed out that that would be a clear thing for classical. If anything beyond that would be quantum. In Bell's case, for example, you saw 2 root. So you are going beyond quantum. That is what we are being tested. But it has foundation in statistics, which was very powerfully developed by many people. For example, yesterday, Professor Davidovich was pointing out that Kramer-Rao inequality based on Fisher's theorem. Professor Rao is still healthy, close to a century. Hope he, and apparently he keeps, doing research even now. You are told person. And this discovery was done where? In Calcutta, ISI Calcutta. Bhattacharya distance was used by, in the works of, what was this? Lakshmana and others, Bhattacharya distance. And that paper was published from ISI Calcutta. Fortunately, Bhattacharya lived very close to the place where I am in, Noihati. And this work was done in ISI Calcutta. Here, Parthasarathi, whose talk will be delivered by, this Ushadevi, he was in ISI Calcutta. And the so-called hypergraph state was discovered in ISI Calcutta. And you can just look up the history of that thing. Parthasarathi and here Rao and Pillai. We are looking at agricultural statistics problem, where the coupled equation became a matrix equation. When you solve, the solution was the hypergraph state. This I didn't know. I was told by Karol Horodocki from Poland in one of the talks in SRI, Correspondence Institute. So a lot of these things, for example, are being used, which was developed in India. Very happy to know that. Now, so therefore, in the 50s, this precise formulation of EPR paradox, in early 60s, this mathematical formulation due to Bell, and then people started working on this foundational aspect, precise understanding. You see many of these papers, came up in 60s. Hullebo, for example, there was a beautiful result. How much information can extract? Came in 70s. Now in 70s, again, computer people started making computers smaller and smaller, thanks to the Moore's law. Because Moore, an engineer who pointed out that the chip size will decrease, become smaller and smaller. So in 70s, it was Landauer who gave very precise formulation in terms of heat loss and information loss. So he really realized that information is physical. So loss of information, half KT is like 1 unit of information lost. So then idea of how to avoid loss, how to avoid heating. Then people came up with this kind of circuit, this 3-qubit, which is control, topically 3-qubit gates were invented without knowing quantum mechanics. And they were avoiding loss. Then when quantum mechanics people came in, they understood they were avoiding loss because they are unitary transformers. Control, not topically gate. But so engineers were already inventing things and applying it on circuit, which are avoiding loss. So it was this loss of heat which led to information being heat. That was the development of 70s. So then people are trying to really go to the quantum domain because chip size are becoming smaller and smaller, few electrons, heating, and hence how to avoid loss. All the 80s, when I was doing my PhD, so Feynman was writing papers on this area, and people were, our professors used to think that what is Feynman doing these days? What is this quantum computation? But now when you look back, you see, this founding ideas that a quantum computer is required to solve real quantum problems. He was encountering problems like confinement of quarks, strong interaction. So we believe that if a quantum computer will be there, it would be better to solve these kind of problems. So he came up with this idea. Now came up this gate. I described to you Hadamard controller, Arthur Perez. And so all the 80s, and this you cannot do any kind of unitary matrix you cannot use, like quantum mechanics cannot be used to make identical copies of unknown states. Utos and Jurek, 82. And so you cannot make a Xerox machine of unknown states. So the restrictions coming from quantum mechanics, because the evolution has to be unitary, the slowly realized from that 1982 paper of Jurek and Utos, and subsequently, there have been development due to Poti, Einstein, essentially pointing out that quantum mechanics has restrictions. So all the 80s, those two crucial papers, Feynman and Arthur Perez, International of Theoretical Physics, laying the foundation of real quantum computers, which is being used now, the so-called universal gates, that using only two simple matrices, 2x2 and 4x4, you can do anything you want. So then still, I remember I was doing my PhD, 82 to 88, then subsequently postdoc. People used to talk. Brassard was in University of Montreal, where I was a postdoc. He gave a talk of how to send key, to develop this quantum key in a ledger, which they had apparently done, so that nobody can beat them. So people used to say that, why don't you then sell and make a lot of money and you are getting irritated, things like that. No, just taking them seriously. Then there are two developments in early 90s. Gruber's search algorithm, then factorization algorithm into this mathematician, Peter Sohr. So essentially, the whole world depends on secretly sending messages and deciphering them. So how to encrypt, how to decrypt. In your bank transaction, for example, if somebody knows your password, you are in trouble. So the huge number of people into research to find out, what is the best way to send secret messages and generate a key to encrypt the message. So key should be known to only two parties, you and your friend with whom you want to share information, and secret information should be shared. So people realize that if you can generate a series of numbers which are random, like 0, 1, 1, 0, known to you and your friend, you can use it as a base. Convert all of your information into numbers, which you can do, like in binaries. Classical computers depend on that.
Excuse me, Professor.
And then you add up this key.
Professor, can you hear me?
Sure, yeah.
Yeah, are you changing the slides? Because it seems like in my system, we stuck in the second slide.
Tell me again, what is it?
Are you changing the slides?
No, the slides I'm still telling you a story. I am not changing the slides.
Okay, then it's okay.
I'm just going through. Before I show you the slides will be essentially a bit mathematical. I'm going through the developments of every 10 years, okay, to point out what are the relevant things. Then I'll just show the slides and share it with you. My point is that what are the key developments which brought us to this far? That's the idea.
Okay. I thought there is some kind of problem in my system.
No.
Okay. It's okay.
So, so this, Grover and Peterslow. Grover's thing, even if you look at now, very simple idea. He was, of course, an engineer, only knew 2x2 matrices, from India, Virat. And very simple man, did not know anything about beyond 2x2 matrices. Use this reflection and realizing that quantum mechanics depends on addition. If I can change the sign, the things will cancel out, and I can actually zoom on to my thing which I require. You are looking for a book, for example, in a library. You wanted a specific state or a specific book. How do you then remove all the others and come up with your own thing? Point is that if you know your own thing, give that information and try to, through interference, namely by putting minus sign, subtract each other and remove the others. So this is basically mirror reflection, parity. So very effective use of this parity, this matrix operation of starting with an unknown state, like for example, all ones on a column vector, zooming onto a given state, like 1 or 0, you can actually do it quite fast. And again, a big matrix was factorized into 2x2 kind of thing. This quantum superposition was used with a suitable minus sign to remove the states. Very simple idea. Just look it in this way. You realize you can zoom on to the state as you want if you remove the others. Removing others is by putting a minus sign and adding them. Beautiful idea. So then, after this came, slowly people became serious and started putting money. Who are the people who put money? Central Intelligence Agency, CIA, USA, and Swiss Bank. Obvious reasons. See, every secret agency would like to send messages secretly. And Swiss Bank, of course, would like to keep their money safe. Who are putting money there, people do not know. Transactions should be very secret. So they have even now also, a lot of money is going there to do research. So what are the technologies that has come out? By now you might have already checked. Quantum random number generator based on measurement, which collapses the state. Then quantum key distribution, already RP Singh has talked about it, also Bosina will talk about it because they are developing those kind of things. Quantum key distribution, BV84, then V84. So those kind of things. Eckhart 4, they are being actually used now. Single photon generator, detector, very powerful detectors capable of detecting single photons. Okay. Entangled photon generator. And those are, for example, these crystals, BBO crystals. Those things are there earlier. The light, for example, was giving us these ordinary and extraordinary rays. So essentially, if you realize, a lot of input has come from the study of light all through the ages. So very good. So then, in early 90s, late 90s, nuclear magnetic resonance, NMR people, they came in. Those NMR machines were built for biology, initially for physics, then chemistry, then biology. So they actually showed that you can actually use them to demonstrate ideas of quantum computation. And people are initially questioning, because Rangit Bhattacharya gave the talk, that you guys are dealing with so many atoms and molecules. Are you really doing quantum computation? So a lot of discussions went on to see as if they are doing quantum computation or not. The so-called pseudo-pure state. Is it really quantum? Now people believe that it is quantum. And they showed, for example, papers like 15 is equal to 3 times 5, 21 is equal to 7 times 3, teleportation in the late 90s. Slowly, NMR people get in, and the early results demonstrating the essential ideas of quantum computation came through them. Now, of course, then after that, a lot of development, significant developments. For example, in India, I went from Hyderabad when I was in Hyderabad 93 to 2002. People are beginning to sort of read quantum computation, getting aware, and foundation, of course, a lot of development from Calcutta. Dipankar Home, Dr. Bose, then Guru Prasad Kaur, it's a very solid group, and small packets. For example, Bangalore, Professor Mukunda, Professor Simon, Professor Subhash Chaturvedi, Professor Srinivasan, Professor Agarwal in Hyderabad. They're studying for the light side, coherent state, their property, things like that. Foundation side was from Calcutta, and there were, other people like, TIFR, Professor Virendra Singh and others, Professor Roy, and they were developing this. Of course, George Sudarshan was all the time there. He was abroad, quite some years he spent in math science also. So early development was basically like that. Then real investigation started slowly all over the world. particularly after this Peter Shor and Grover's algorithm came. And a lot of developments have since then taken place. Now you can see technology has come. Now let me show you, I'll just guide you through these things. Okay, so now let me adjust. So now Schrodinger, Heisenberg, Dirac I have shown. This equation, for example, you are not familiar, except that this notation is that K, function of time. So this is the evolution equation. Now Schrodinger picture. What is this picture? Because you will encounter when you are solving some problems, wave function is time dependent. H is the operator, here it is Hamiltonian, and it is not. So this evolution, for example, can be used to find out the eigenstates. Like for example, yesterday, Devasis was telling you the variational eigenvalue solver. How can you use to solve it? D-Waves is a quantum computer which uses a evolution, on an Ising kind of system, Ising model, spin model, where the problem which you want to solve is stored in this Hamiltonian. It evolves and after some time settles down on the solution, adiabatic quantum computation. So the Hamiltonian has multiple roles. It evolves the state and simultaneously can do quantum computation if you can use it very effectively. For example, you have seen weak measurement. A very weak coupling here between the system and the state can actually measure the value very accurately, as has been shown in weak measurement. So this Professor overall pointed out, the interaction Hamiltonian has information about time. Namely, there are different steps. If you go to quantum mechanics, read it carefully, that there are between T0 to T1, T1 to T2, and Professor overall pointed out, those things can be very effectively used for quantum generating quantum technology. This talk if you go, you see those things. So the Hamiltonian and time evolution has to be taken very carefully. Okay, so now, so there are these pictures. Sometimes when you solve, you make the wave function time independent. You deal everything with operators, namely operator becoming time dependent. So that is the Heisenberg picture. But as usual, synthesis is the best way. That both the things have its advantage, and it was Dirac who pointed out that if you use both of them, namely your Hamiltonian has one part which you can solve. For that, use the wave function to be time independent. That is Schrodinger picture. The part which you cannot solve, so that part you deal with using Heisenberg's approach, and that is actually optimal. And that is what Professor overall used while describing this system. Now, when you do that, you will find out the time gets split into different domains, and that you can even now control effectively and leading to some kind of quantum technology, as this talk was pointing out. All right. So now these 2x2 systems matrices which you encounter in spin, which earlier came in the description of light, upon this polarization, and number system called quaternions. They all depend on this matrix. Identity, sigma x, sigma y, sigma z. States, eigenstates, 1, 0, 0, 1. So this is our qubit now. Matrices. We have linear vector space, therefore superposition is true. Unknown state, if you do not know alpha and beta. How to send an unknown state? The state doesn't go, information goes. So teleportation was done in theory 1902, experiment around 1999 or something. Now, for example, teleportation has been done with large extent that you can send it distances like 500 kilometers or more across the river Danube in different laboratories. So there what happens that the information goes alpha, beta on the other side gets recreated. State 0 and 1 doesn't go. But when it is recreated perfectly. There is no mistake. So one of these tutorials, maybe either me or somebody can work it out. It's a beautiful application thanks to the engineers. Again, Bennett, Brasser, and others who showed that this quantum entanglement, the abstract thing which gave to EPR paradox, can be very useful for sending quantum information or recreating state, unknown state. The sender does not know Alice what state size, Bob does not know. But if the protocol is successful, unknown state goes from here to there. State doesn't go, information goes, it is created there. Exactly. Alpha, beta, no mistake. That is the amazing thing about quantum. In this process, you use something called LOCC. Okay. Local operation, classical communication. What is local operation? Alice will be sitting in Delhi doing some manipulation using matrices. Bob would be sitting in Washington doing manipulations on his side. Entanglement doesn't get affected. And manipulations will take place based on experimental result in early site, communicated through a classical channel like a telephone. So local operations and classical communication. Classical communication is telephone, is the one which will be created. So as engineers do, they precisely pointed out in this process, you will lose 1 E bit of entanglement, it will cost, because entanglement is cost. To maintain a channel is cost. 1 E bit of entanglement will be lost. 2 C bit it will cost. That much money, telephone conversation. And you can send 1 unknown bit state, it can be created on the other side. So that is the cost. So besides thing, we work out on the larger bit later. All right. So gate, we had pointed out, there are only 2 gates which are universal. Hadamard and control not. This I introduced to you. But for convenience, if you want to change the state from 0 to 1, 1 to 0, you use X gate. If you want to attach a specific phase, they're all single qubit. You can apply Z gate. Very good. Now, Hadamard I have introduced just for the sake of completeness. You can see here. So there I had left you with a problem that if you analyze this matrix 1 by root 2, 1, 1, 1 minus 1, you can see 1 by root 2, 1, 1 is the eigenstate of sigma x. 1 by root 2, 1 minus 1 is the eigenstate of sigma x with eigenvalue minus 1. Now this u can be used to diagonalize that matrix sigma x. But if you put it in the form of 1 by root 2, 1 minus 1 and 1, 1, it is not a unitary matrix. I had asked you to check. If you would have checked, you will find out this fourth power of this would be identity. It is like, this square root of I, the matrix language. Those things can be useful. Square root of this kind of thing would be useful because if you want to attach a phase square root of I somewhere, you can use these kind of things. So work it out yourself. Now you will find out that these are analogs of light, linear polarization, plus minus 45 degree, 135 degree. So light had all this information earlier. Control lot, for the sake of completeness again, I request you to find out these eigenstates, eigenvectors, check what it can do for you, because whenever you see a matrix, find out immediately these eigenvalues, eigenvectors. That will give you how to diagonalize it. That will give you a lot of information about the system, and it will bring familiarity to you. Control lot. So now you see detail as control X. You see that is called 1, 1, then 0, 1, 1, 0. 0, 1, 1, 0 is X. What it does, it flips the second fellow. So those are the things which are used. This circuit I had worked it out for you. Hadamard control lot and measurement leads to an entangled state, particularly Bell state. So 1 E bit of entanglement you can create through superposition and this. Superposition is through Hadamard, it's called parallelism. It gives power to quantum computers. Control lot is entangled thing. You can use more than 1 qubit to solve some bigger problem, like for example teleportation. All right. So this I had, the EPR paradox I had mentioned to you, that has kept people occupied since then. Only when engineers came, this has been used, but even now also people are debating it. Essential point is that Alice and Bob. Now, first of all, how do you create this kind of object? You could take a particle called pi naught or an exciton. If it decays into 2 photons, one goes from this side to that side. And if the state, for example, is a singlet state or a triplet state with 1, 0, angular momentum 1, spin projection 0, you will find out these particles are correlated. They are actually examples of Bell state. Now, of course, you can create them in labs. So that means people take this kind of thing, test quantum mechanics. Because Bell would sort of formulated this very carefully using these 2 by 2 matrices and the ideas of Boole from classical statistics. So many careful experiments, even now also, to check, to know all this loophole-free. Even now also there is huge debate. The person who formed the statistical analysis part for loophole-free test of Bell's correlation is now engaged with another scientist who is trying to show that this correlation exists because the space is of a peculiar kind, not due to any quantum mechanical correlation. So you can see a lot of debate even now also is going on. Various kind of loopholes to avoid this kind of correlation coming due to other sources. people have, as somebody was pointing out, people have taken light and from Zeilinger comes from quasar, far away object, expecting and from cosmic rays. So there should be no correlation. To all extent, people have gone. There one experiment involved 1 lakh, more than 1 lakh volunteers from all over the continent, giving input to 12 or 13 experiments of different kinds, just to rule that human will, human consciousness is not controlling this correlation. They're indeed there very recently. So lots of different experiments are still going on to check to what extent quantum mechanics is giving correct answer. Now, so in quantum mechanics, you saw, this superposition, namely, the state clause is composed of zero or no. You see classical logic, they are like yes, no, maybe. That maybe kind of thing is there in quantum, which is the superposition. So now, Alan aspect in early 80s is the person who did that experiment, 1982. Some aspects of it was actually done in Rochester, Professor Mandel, where I was a student. I had heard about that. Alan aspect and Mandel's group were the two big groups, dealing with things at single photon level. You have heard about the Hong-Mandel parameter. So many parameters came to quantify what is quantum, and then intensity correlation, showing that if it's quantum, it will show some anti-bunching or bunching, which is not there in the classical world. So people are still trying to analyze what is quantum, how do you check what is quantum. And it was an eye-opening experience for me because this 2021 paper, physical evidence paper, if some of you are curious, we can send it to you, where Vogel, VOG is a co-author, showing that through Sudarshan's P function, this flow is quantum, but doesn't have any other quantum correlation. I still don't understand how it works. And they of course, took light to clear the state. Very beautiful idea. So, and you see this Bell seeding quality, you can see this kind of statistics idea, which you have heard, for example, Professor McComb pointing out, they were the kind of ideas, mutually exclusive event and things like that, which was generalized, statistics from classical statistics, to show that quantum is something more. Okay. So these are the kind of, experiments people are seeing. 1 lakh participants, online video game, 12 hour video. And, it's just amazing, 13 different kind of experiments. So that human choice, contradicts different human choice. Just avoid that. This kind of correlation is not coming due to human choices. All right. So now one simple question arises. If some of you are curious, you can work out this paper. So that question is that I have a big quantum computer which has, in entangled state built into it, like with a side. And as you know, due to the coherence, it can decay. So how do you know that the quantum computer is working? So what we pointed out with this boy, Monu Gupta, that you can actually extract information from there, sitting on this, so-called states which are outside the quantum computer, and apply the Hadamard quantum law. So this ancilla get do the reading. This RO is for reading. You can actually extract information and check if the state is there or not there. In the process, you are not affecting the state. Psi remains psi. But through measurement, you can actually read that yes, the state is intact, quantum computer is working. Otherwise, some person may touch it and the quantum computer is gone. Environment may have the coherence also. Fortunately, so there are 4 Bell states. This kind of thing. These 2 appear naturally in nature, singlet and triplet states, para and orthohydrogen. They have to be created. And in NMR, nuclear magnetic resonance, that's what I was telling, they can be created starting from pseudo-pure states. That was thanks to, and their Hamiltonians are all the spin Hamiltonians. These are the kind of Hamiltonians. For example, D-Wave's computer uses rising type of systems. So they're actually practical. You can actually use them. So to our good luck, Professor Anil Kumar, this is the paper, 2010, used nuclear magnetic resonance. So starting from pseudo-pure state PPS, created Bell state through Hadamard and controller, and then measured it and showed that what the thing which they proposed, you can in fact extract information and yet leave the state after readout intact. So these are the steps involved. NMR to be difficult for me to understand, but it works. Okay, so and words you will encounter PPS, pseudo-pure state. And these kind of things, applying control law is done through the radio waves. Okay, control law, the phases you can supply. So all those things you can actually do and two-spin interaction. And you can actually make these optimal. There are algorithms available. So it's a very sophisticated thing. Up to 13 qubits apparently they have gone. Even that's difficult to maintain. But even that also has thrown a lot of light on this thing, quantum computation. Okay, so now as I was telling you, now in metrology, for example, you want to measure things very accurately. There was a very beautiful paper by Jurek, lecture paper, which showed this cat state. This what you have seen here is a cat state, localized in the momentum. It can actually show both particle and wave nature. You can see here, particle is localized. It's like a particle. There's interference here in the domain, which is very quantum. Why quantum? Because linear function is very negative there. So particle and wave nature can show simultaneous manifestation. And again, this can be used for technology. You can actually use this for very accurate measurement of coordinate displacement and momentum. What happens if you displace, this fringe will shift, and that can be measured. So there was a paper, physical emulator, around 2007. First author is Prasanta K. Experiment was done in Poland, where actually it was shown that the frequency accuracy is, sub Fourier. Namely, it can be more accurate than what Fourier space can give you, sub Fourier sensitivity. So cat state can be used for metrology. Professor Davidovich was talking about metrology. The more sophisticated state called cat state will give rise to much more accurate thing. You had heard about Heisenberg limited measurement. Uncertainty or going beyond short noise limit 1 by root n to 1 by n is achieved here, where cat state. Two states localized in momentum space and coordinate space. So very peculiar interference can give rise to very accurate, measurement. And these are actually, now this was 2019 paper, has been created in the lab, very robust, doesn't pay, and very accurate, again through optics. So this thing, cat code thing has now been created. There's a code called cat code, again from Yale, experimentally realized, which can actually do quantum computation. And this is for metrology, very accurate measurement, sensing. And eventually this can also be used for designing of quantum circuits. You can see particles will always go to the place where there is no light, or there is light, you can use for designing of quantum circuit. And this state which I am showing you, this so-called high Q state, has been realized experimentally, 2019. Maybe that now technology. So as I told you that the unknown state can be teleported. It's 1400 kilometers between China and Austria. Pan is the researcher here, J.W. Pan, whose name has come up many times, and Anton Zeilinger, Professor Zeilinger in Vienna, who was the supervisor of Pan. So one should have students like that, which will communicate to you wherever they are. So these are the kind of things. These things you see, they're all optics elements, half-wave plate, quarter-wave plate, through light. So eventually, silicon and light, they are coming into play, and hopefully tomorrow's quantum computer will be designed through them, which will very nicely interface with classical computers. So this kind of circuit, Zeilinger is the person used this Q-trit, where Q-trit means 1, 0, 0, 0, 1, 0, 0, 0, 1. 3 states. In principle, it's called Q-dit, D states. So they could create fidelity. This is what you will see, how accurate. So this is the circuit. Again, you see, beam splitter, BBO crystal, half-wave plate, quarter-wave plate, all through light interference. Okay, so now this is quantum field distribution. Bennett and Brassard sitting in Bangalore in a conference with beers in their hand, discussing this quantum thing, what they heard about the measurement collapsing. Very weird. Can we use it? And this is the first protocol where just measurement method has been used in 2 bases. This is your linear basis, 2 state, 1 x direction, 1 y direction, 45 degree and 135 degree, and collapse. Those things, if you can do just measurement, you can actually, create a key which hopefully you would not know. How will you check if? Because by talking to each other, they would know this is the outcome they're expecting, But because you have measured, you have changed the state, therefore that outcome somebody is there. So they discard generality again. Only when they're sure that nobody has seen it, they generate a secret key, and that key is used for encryption and decryption. Beautiful algorithm. All right, so now satellite, you heard yesterday that China had put a satellite. So now, optics. Optics is the thing through which quantum key distribution, teleportation, which is going on, very accurate. All right. Now, as you see in your weak measurement, this thing which Professor Vaidnan was pointing out, it allows you very accurate measurement of small fluctuations or small variations. Those are actually second chapter of quantum mechanics, strong galactic device. So believe it or not, 0th chapter, first chapter, second chapter, those are all those things which we are using with Pauli matrices and doing quantum computation, coming up with algorithms, and nothing more you need. So if that has given Grover a Grover algorithm, then it might as well give you something. So you see, these are these chemistry labs, chemistry bridge. Chemistry people are actually now using it very extensively. All the chemistry people to very accurately find out the energy levels of excited molecules, their simulations, drug designing, how to design drug molecules, those experimentally. Okay, Professor Gosisina will talk more about this. She is involved developing this. They have communication protocol in collaboration with Canada. Here is our rover, love rover from Iraq. Very modest man. And people believe nature probably is using this in many of these things like photosynthesis. A very simple idea, you should play around with it. Yeah. Now in quantum computation and bringing this computation into the domain of quantum domain, Professor Bhadirani from Berkeley, University of California. So he is the key person. Google Supremacy implemented his idea. Now IBM, you will see more of it. And there are many things available now. There are private companies, ID Quantic, Toshiba, MagicQ. They're selling things. Okay, so price range is here. If you have money, you can buy now. All right. So now, two distinct ways are now being employed. This so far is technology. Some of it is going towards technology now. People are shown in the laboratory. But I'm pretty sure very soon they will also become available. There are, packages like Jandao, which is implementing optical kind of things. But this is the one which is primarily being used now. Now, I would like to mention that about Professor Sudarshan, because each PP function is being used for testing quantum nature. Professor Sudarshan passed away, and this coherent state you have heard, what is going to come. Inventors are Glauber and Sudarshan. Glauber is fortunately still doing well. Now, those are the ones which are being used now for quantum computation. Now, they measure analogs of coordinate and momentum, which are called quadrature operators. So, what you can deal with the mathematics is very simple Gaussians, as you know. Now, these are this, for example, using strawberry fields and now you can actually simulate them. Okay. So, you heard about coherent state, cat state. They're all built from Gaussian functions. Squeeze state, for example, squeeze coherent state, both this is like a circle. If you make it an ellipse, it becomes a squeeze state. All right. In this cat paradox, it has led to lot of new ideas, and now the cat state also. Again, cat state was used for quantum computation in the hand of engineers. It was started by Schrödinger in 1935. And Wigner function has played a very key role because Wigner was very worried about this non-commuting object like XP. But he came up with an idea where X and P are just like numbers. You deal with this object, and like statistical mechanics, you can phase space, you can describe everything. All the information is there. And XP are not commuting objects. So that was quite nice. Negativity of Wigner function leads to quantumness. But it's not that squeeze state, it is not negative, but yet it is quantum. That comes to P function, Sudarshan's P function. That is Sudarshan's contribution. As you saw yesterday, by looking at the statistics of light, intensity correlation, you can actually check that it is quantum. Okay, so some of these things have been already explained. Vivek also explained a few things. So I will not get into details. Coherent state is again a Gaussian. So mathematics is not very difficult. And these are the parameters which were used to check nature of photons, subposition and superposition. That is how they check quantum mechanics. Okay, so now how does CAT state? I showed you some interference pattern. You can actually work it out. So Gargi, for example, showed you how, and Orman answered many of your questions. So, all right. So let's not get into any details because these interference phenomena. If you add photon, what happens? One of them, then two of them. How much you can distinguish? That is leading to a photon addition, and how do you distinguish them? Can actually make hopefully give rise to better metrology, sensing, and detection. Metrology, sensing, and detection. These are the areas where hopefully they will find application. All right. So now, and they all show their differences at when the photon number is low. When photon number is high, it becomes regular classical behavior. That's what it shows. Okay. So Alok is probably there. You know, you can actually see this some small areas in phase space showing structures like soft Planck, very counterintuitive. Everybody thought H bar is the lowest volume, lowest area, but actually there are structures below that because Jurek pointed out, and their connection with this weak measurement which Professor Weidman was there actually can be worked out using Wigner function. Now this is this huge cluster state which was created, in Denmark Technical University, which is leading light-based quantum computation. Then China, as was shown you by Professor Chen yesterday, has created this big supercomputer with a huge number of light sources, showing quantum supremacy again. All right. This is Google's chip that has been already told you. Professor Bhadirani's work played a very key role. All right. So now, okay. Now, many universities are getting into it, and the, now the design is how to create a chip, silicon, with, at the nanoscale level, so that the whole thing gets into a silicon and photon kind of domain where a regular computer type of can be built. It will interface with this whole classical computer, and together they hopefully will produce powerful computers. Okay. Now, error is a problem because many of these things, for example, has a lot of errors. So how to avoid error, how to use the technology so that money is generated. So lots of companies are now coming into play. Even Singapore Center for Quantum Technology as a private company coming up with small design of satellites. Some of them are already up there, China, Japan. Okay. So now you may think that what can you do? So believe it or not, everybody can do something here. So there was this teenager who after high school came to University of Texas. And so she was shown a very powerful paper by, this thing, using so-called singular value decomposition. Professor from MIT, there's some problem. So the quantum recommendation problem can be solved only in a quantum computer quite fast. She showed, looks like Sudoku game to me. I can use a classical idea to solve it, and that's what it showed. You can check. Now, if 18-year-old, if she put the paper, I think paper has been published. If she can do it using her idea of matrices and vectors, why can't you? Now, computer science person, student of Professor Bhadirani, Urmila Mahadev, 8 years, try to prove this thing. Suppose somebody says, I have a quantum computer. How do you prove or disprove? Keep on asking questions, get the machine give you answers, and you can actually prove a very powerful result. That's something with a quantum computer. 8 years, one paper. Very recent one. Now, the really internet, quantum internet design, quantum network design are in progress. You can check, for example, one Indian person from Northwestern University, Evanston, is actually the key person behind it. I will leave it to your curiosity to find out. China already has that kind of thing. So your younger generation to take the challenge and come up with new ideas, new network, new algorithms from here. Right, thank you. You can ask questions now. Questions in chat. Maybe some of you can open and ask questions if you have. Yeah. How is light or photon controlled in quantum information and computing implementation? Like when teleportation is of one unknown polarization state of photon with two entangled photons, how one does this? Now, see, photon, fortunately, still has energy conservation, momentum conservation, it obeys, angular momentum conservation. So, if you, for example, measure at some place and you find it as angular momentum projected as +1, and it's an entangled state of plus or minus, the other fellow automatically will be minus. You can measure its energy accurately, as I told you, single photon creation and single photon detection. When I say accurately with uncertainty, delta I, so now there are actually things to manipulate the polarization, the momentum, and energy. So those things are possible now. Achha, so, okay, the other question is by Kamlesh. Kamlesh is from Hyderabad University. How are gates like Hadamard gates better than normal logic gates and universal gates, and also can be Hadamard gates using logic gates and vice versa? See, if I believe you are talking about classical gates as logic gates. Hadamard was, honestly speaking, really no difference in the sense that it's a unitary matrix and produces superposition. When you have analyzer, polarizer in light, you actually more or less using the same thing. Okay, so mathematically there is no difference. Linear algebra, vector space. Now, when you implement it, for example, NMR people, they would use so-called pi/2 poles, okay, to create superposition. So therefore, implementation at the quantum level, everybody has their own way, but mathematically there is nothing very big deal. Quantum knot is truly quantum, but others are not. Is there something like universal gate? Yeah. Universal gate is this Hadamard and quantum knot. You can input other gates, but these two are universal. That was after Paris. If there was no superposition, would there be entanglement? No. If there is no superposition, there will not be entanglement. You need. There is a very interesting question. I'll leave it to you. Now, question is this, that you take two terms, as you saw, 0, 0, 0, 1 plus minus 1, 0 by root 2, maximum entanglement. You are three of them. You find entanglement will decrease. It's still not very clear how many terms superposition you should take for maximal entanglement. Okay. And all these entanglement measures are still not very good and very accurate when you go to more than 3 particles. 3 particles, we have some reasonable understanding. 2 particles, complete understanding. 3 particle entanglement, some reasonable understanding. The new concepts like monogamy, and other things are coming in. Reasonable understanding, W state, GZ state. But still there are surprises, because 3-body correlations are still a surprise. But beyond that, nothing is understood. So, if you have any idea about matrices, vector space, and you know how to take trace, those kind of things, you can still contribute quite meaningfully. So no superposition, no entanglement. But one more thing, you can actually, let me partially correct myself. For a single photon also, you can actually entangle its polarization with its momentum. But for that, in those degrees of freedom, you will have superposition. But the particle is single. So as you know, for example, Dirac pointed out, a single particle can interfere with itself. So this is possible. Yeah. Okay. Classical computers have 3 stages. Toffoli gate. That was implemented in a classical computer. 3 gates. Yes. Among the light-based on spin-based quantum computation, which has more potential. See, it will be now these companies are coming up with silicon and photon. So if you ask me, I am involved with a collaboration with some Italian group, with Professor Gossicina, Dipankar Home, Prasanta K, and this group is in Italy. University of Trento, you can go to the website. They have actually a patented technology of silicon, and which hopefully will be reproduced. And they have input from Professor Gossicina's lab here, and that will be achieved. That is the kind of thing people are believing. So quantum dot-based or silicon-based kind of thing. And I am a theorist, so I am seeing them and I am just answering. Maybe I am completely wrong. Is the double slit experiment direct evidence of superposition? Yes, right. If you see, that is where they test now. If you have double slit, if you measure on which slit it is going, then there is no interference. So you can please read Alok's paper, where Professor Halliwell will be giving a talk and ask these questions to him. And also Professor Qureshi. Qureshi has a lot of interesting papers in this area. Yeah, thank you. Thank you. Yeah. Oyan, what are you asking? Oyan, why are you bothering me? Because you should be knowing this. Okay, thank you. Because you did light-based thing in Italy, right?
Yeah, thank you, sir. Yeah, but it was very exciting listening your talk. It gives a big overview of what actually is happening. Thank you, sir.
Okay. Is there some literature on entanglement between two parameters? So yeah, that is. There's a very good review article. We'll put it in our, we'll now create a place where those things will put. Very review articles from this University of Trento. You can go to University of Trento, go to their site, a beautiful review article. And that is the latest actually. Professor R.P. Singh's lab also has some experimental results on that. And I think Professor Ghosh will be talking about that also. All right, thank you. Now, if there are no more questions, are there any other questions? No, right? Okay, good.
Sir, can three-body problem solve, sir? Like three-body problem in...
No, not exactly. Not exactly. Some three-body problem can be solved exactly, not everybody. You know this Poincaré is the person who pointed out the difficulty of solving three-body problem.
Yes, sir.
For example, instead of Kepler problem is 1 over R, like Coulomb problem, with 1 over R square, you can solve three-body problem. So like, for example, harmonic oscillator with 1 over R square interaction, purely 1 over R square interaction, and purely harmonic interaction, you can solve three-body problem. But the answer is in general, no. For example, our Professor Santhanam was pointing out, Professor Aru Lakshminarayan and his students have solved a three-body problem, this quantum kicks and things like that. But the answer in general is no. Classic example is Kepler problem, three-body Kepler problem, no. You know the beautiful history about three-body problem. Poincaré apparently claimed that he has solved the three-body problem, and he published a paper, and then he realized his mistake. Then he sold his house, spent the entire money to bring back all those volumes and destroy them by burning them. You see to what extent people go to keep their reputation intact. Good morning. Why good morning? Where are you? Sudipto, Padi. I thought it is lunchtime. Yeah, Pradeep. While implementing certain arithmetic operations in IBM quantum computer, how can we implement decimal numbers? Yeah, that you write it in these computer people, engineering people should know better than me. You can actually implement. You write in the basis of that's just like standard things. I cannot tell you exactly because I see my students doing it. So maybe you can ask this question to Vikas Behra or Shreya Banerjee, and they will answer you better. But I have seen them implement it. You can in fact this IBM quantum people when they come, there are 4 or 5 talks at the end. You can ask them. They're very helpful. They can help you. But best thing is to ask Shreya Banerjee.
There are no more questions.
All right. So there are no more questions. Thank you. Okay. So,
sir, can I come in?
Yeah. Ask.
Utpal here.
Utpal. Yeah. Show your face here. Where are you?
Yeah, I've switched on my video now. Am I visible?
You are. Yeah. Yes.
Okay.
Yeah.
Sir, actually, just like we kind of do with photon-added coherent state and maybe photon-added cat state to have kind of sensitivity analysis and quantum metrology, can this be done for atomic coherent state?
Yeah, I think
is there any experiment or theory somebody has done for cat state also?
See, photon, I have not seen it. Honestly, I have not seen.
But I guess that should be possible because a similar situation can be built up with atoms as well.
Okay, I would believe so. See, but there having single atom level accuracy would be difficult, no? What do you think? Until and unless you have a see, in case of these resonators, what they do in case of light, they will send high Q cavity. They send an excited atom. If the atom comes in the ground state, they know one photon has gone there.
Right.
That is how they check this coherent state, photon added coherent state.
Right.
Photon added cat state, single photon added cat state, they check through parity. That's an experiment, 2019 experiment. It becomes immediately parity odd. So they can actually bring it back to parity operation. So the parity really distinguishes them. But but I think that for example, in this atom cavity kind of thing, now they are coming up with this high Q kind of thing also, equivalent high Q kind of thing, right? That is that it may be possible, but to my best of my knowledge, I have not seen it actually.
Because that paper by Professor Agarwal, that weak measurements with atomic coherent states, I think there can be a good analogy with this photon added coherent state with weak measurements also. Following
if it can be done, sure.
I'm just worrying about it and wondering, and then I thought I'll get
that should be possible.
Yeah. Okay, sir. Thank you. It's so nice talk.
Thank you. Yeah. Okay, so I think now, so we can call it a day now. So we'll go for lunch and come back. Thank you once again for sparing your time and listening to me. You can give input to me through my email. Okay, thank you.